In this lesson you will learn how to segment satellite images through SAMGeo, segment anything for geospatial data, model. In Lesson 5 we saw how to train a neural network model to do semantic segmentation, that is to categorize each pixel of an image. In this new lesson we will explore a model called SAM that allows you to generalize this task across different images. In particular we will see how to set up the local environment in order to have a working notebook to be able to test SAMGeo, an open source project that aims to adapt SAM model for the segmentation of geospatial data as well as other geospatial libraries. The link to the GitHub repo of the amazing SAMGeo project can be found in the description of this video. The SAMGeo model is an adaptation of the Meta AI Segment Anything model to ease its use over geospatial data. It could be used to segment, delineate, or label landforms efficiently when using large-sized geospatial raster images. You will find full reference to this model in the description. SAM model has the ability to perform complex image segmentation tasks with unprecedented precision and versatility. Here are some key innovations of the SAM model. Zero-shot inference capabilities. SAM can accurately segment images without prior specific training, a task that traditionally requires tailored models. Inspired by NLP foundation models, the creators of SAM took inspiration from recent developments in natural language processing, NLP, with foundation models like GPT and BERT. Ability to process multiple prompts. You can hover or click on elements, drag boxes around them, automatically segment everything, and create custom masks or cutouts. For this tutorial you will need to have several packages installed as well as GDAL on your system. On my side I'm personally running a Docker image with all needed dependencies. I found quite tricky to have GDAL installed on our operating system together with Python GDAL, but if you don't have this problem you could simply install all needed dependencies in a virtual env. Firstly I'm going to show how to build the Docker image with needed dependency, run it and run your notebook inside it. This helps avoid any conflicts with your operating system. If you're a beginner and you want to learn more about Docker, I have an old video I did about an introduction to Docker. I highly suggest to follow it. The approach I'm going to explain you imply that you have Docker installed on your machine. First of all let's decrypt the Dockerfile that can be used to build your application. From ghcr.io/osgeo/gdal:/ubuntu-small-latest. This line specifies the base image for this Dockerfile. It uses an official Python runtime image provided by the open source Geospatial Foundation, OSGeo, that includes GDAL, Geospatial Data Abstraction Library. The base image is built on Ubuntu and is tagged as Ubuntu small-latest. env Python and buffered 1. This line sets an environment variable pyt to a new nbuffered to 1. This ensures that Python output is sent directly to the terminal without buffering. Workdir app. This sets the working directory within the container to app. Copy. App. Copies the contents of the current directory, where the Dockerfile is located, into the container's app directory. Run apt-get update y. Updates the package lists in the container to ensure that the subsequent installations use the latest package information. Run apt-get install y python 3 pip and apt-get install y libgul1 method glx. Installs Python 3 and pip package manager in the container. Also installs the libgul1 method glx package, which might be necessary for graphical applications that use OpenGL. Run pip install upgrade pip wheel. Upgrades the pip and wheel packages to their latest versions. Run pip install gdal $gdal config version. Installs a specific version of the gdal Python package. It uses the gdal config version command to determine the gdal version installed in the base image. Run pip install no cache dir requirements.txt. Installs Python dependencies listed in a requirements.txt file. The no cache dir option is used to avoid caching the downloaded package. You have now to build your Docker image. The building will take several minutes. On my side I've already done it. Let's now run the container in an interactive mode in order to enter it and run our notebook. Here we're inside our Docker container with all needed dependencies for this notebook. Let's navigate to the repo with our code. We can now look at our notebook. We need first of all to import the libraries. By using leafmap library we can display a specific area of interest. You can also add the map layer you prefer. Here we're going to use a satellite view. In the next cell we check if the leafmap map object M has a user-defined region of interest, ROI, bound set. If a ROI is set, it retrieves the bounds using m.user_ROI_bounds. If no ROI is set, it assigns a default bounding box to the variable box. The TMS_to_geotiff function generates a geotiff image based on the specified TMS source, bounding box, and zoom level. The resulting geotiff image will be saved with the file name satellite.tiff. The TMS stands for Tile Map Service and it is a standard for serving maps on the internet. If you want to have more details, I've added to the code a brief description. The next cell is used to display the image on the base map. In the next cell we're going to instantiate the SAMGeo model for image segmentation. If you read the code description on GitHub, it has several models. We're going to use the one called vit_h that offer good performances. When instantiating it is going to download it. Generating masks is particularly easy. The masks are going to be stored on the disk with the file masks.tiff. You just need to specify your source and output. Additional optional params are for instance foreground and unique. Foreground weather to generate the foreground mask. Defaults to true. Unique weather to assign a unique value to each object. Defaults to true. The unique value increases from 1 to the number of objects. The larger the number, the larger the object area. In the next cell we're going to show masks we calculated previously. If you prefer you can overlay the masks to the base map. If you prefer to have the masks in vector format you can use tiff_to_vector method. We've seen how to run segmentation with SAMGeo model by using default params. But if you prefer to use custom params you can pass them directly to the SAMGeo model constructor by specifying the input argument sam_args. I'm not going to repeat again the masks generation, but if you're interested you can uncomment the subsequent sections and try to run them. We have reached the end of this lesson. I hope you enjoyed this video and see you soon for more content coming.